Welcome to another video for chemistry. In this video we're going to do some word problems using ideal gas law. So let me just quickly discuss how we derive proportionality constant. We derive this by having all of our variables that are changeable into the left side of the equation. And our variables at this point are at the STP, our standard temperature and pressure. And once we do the math for that, we end up with a proportionality constant. So this number does not change. It's kind of like your C in physics for speed of light. It doesn't change. It's always a constant. Now, with some of the problems that we're going to be dealing with, at least in this particular video, are problems in which we start off with something and then we end up with something else. We have an initial and then we have a final. Okay, and that's symbolized by the subscript 1 and 2. The 2 will indicate our final product, and the 1 will indicate our initial, our starting product. So we start off with a set of conditions where we might change something. We'll alter either the pressure, volume, temperature, or the amount of moles that we're dealing with, and then we end up with a final product. Okay, and that's what we want to do. We want to figure out what we end up with based off of how how we altered it initially. So let's take a look at what we're talking about here. So an inflated helium balloon with a volume of 0.55 liters at sea level, which is 1 atmosphere, say we have there a volume and we have a pressure, this is allowed to rise to the height of 6.5 kilometers, where the pressure is about 0.4 atmospheres. Assuming that the temperature remains constant, what is the final volume of the balloon? So when you read these problems, you got to read carefully. What are your givens? What are the terms that you're being given? You're being given a volume, you're being given a pressure, and you're also even being given a height. But if you go back to PV equals nRT, our ideal gas law, there is no term for height. So, what does that play into it? Well, if you keep reading, it tells you what the pressure is at that height, which is 0.4 atmospheres. So then that means the 6.5 kilometers is a negligible, it's an extraneous piece of information you don't really need, because now you know what your final atmosphere is. Okay, so, and we also find that we're looking for a final volume. Okay, so the amount of gas inside the balloon and its temperature remain constant. So the T is going to remain constant, but both pressure and volume change. So what gas law do you need? Okay, so again, this is ideal gas law. Now, I determine the ones that I don't need. My volume, or not my volume, sorry, but my moles remains the same. It doesn't indicate anywhere in the problem that I changed the number of substance that I was dealing with. The moles remain the same, and it also explicitly said that the temperature remains constant. So that means these terms I don't need. I can go ahead and ignore those for now, and then this is the equation that I'm dealing with. Okay, my initial temperature and volume equals my final pressure and volume, sorry, not temperature. Okay, so I want to see what my initials were. I started off with 0.55 volume and at 1 atmosphere. And then I ended up with 0.4 atmosphere, and I want to find out what that volume is. So this is what my equation turns into. 1 atmosphere times 0.55 liters. My initial conditions must equal my final conditions. 0.4 atmospheres. And then I want to find out what my final volume is. So I do some arithmetic. I divide by 0.4, put it on the other end. My atmosphere terms will cancel out, okay, leaving me with liters, which makes sense because that's what I'm looking for is volume. So I do a little bit of math and I find out that it's 1.4 liters. Okay, now that actually makes sense when you think about it, because at 1 atmosphere, going from 1 atmosphere to 0.4 atmosphere, my pressure has been lessened. So if I have less pressure pushing on the balloon, then that means that the balloon can expand even further. And it expanded from 0.55 liters to 1.4 liters. So this makes sense. My math was good. My logic was good, so I'm happy with that answer. All right, let's take a look at the second problem. Argon is an inert gas used in light bulbs to retard the vaporization of tungsten filament. A certain light bulb containing argon at 1.2 atmospheres and 18 Celsius is heated to 85 Celsius at constant volume. So the volume is constant, doesn't change. My atmospheres, my pressure is what I need to figure out, is calculate the final pressure. Now look at my temperature. It went from 18 to 85 Celsius. So again, I need to determine what I need and what I don't need in this particular problem. And I determined that my volume is not a player in this equation, and my moles is not a player, but my pressure and my temperature are. So this is the equation that I'm dealing with. I have initial conditions and final conditions. And let's highlight those conditions. So 1.2 atmospheres, and then I want to find what the final pressure is, and then I have 18 and 85 Celsius. But there's a problem with this. If you recall, STP, standard temperature and pressure, our temperature, the unit for temperature is not in Celsius, it's actually in Kelvin. So I need to change that. To change Celsius into Kelvin, I need to add 273. Okay, and that gives me 291 and 358. So now I can actually do my arithmetic. Okay, so my initial conditions gave me 1.2 atmospheres. I divide that by 291 Kelvin. And I also want my final temperature, or my final pressure, so I need to eliminate my temperature on the right side and move it over to the left. And by doing that, I multiply it. And now it's just a simple arithmetic, and I end up with 1.48 atmosphere. Okay, so I end up with more pressure, which makes sense. Because if I started off with 1.2 atmospheres at a lower temperature, when I increase the temperature, that means I am adding more energy into those molecules, which is causing them to speed up even more. I increase pressure. If you go back to our previous video with our intro in gases, or our pressure of gases, that is, you'll see that when you add more energy, you increase the velocity, you increase acceleration, which means you increase the force, which finally increases the pressure of a system. So I went from 1.2 to 1.48, an increase in pressure due to an increase in temperature. All right, so that does it for our word problems. I hope this helped, and we'll be dealing with a lot more in class. So good luck with your study.